So welcome to class for Wednesday, April 29th. The end is near, folks. We've got 5 classes left, so prepare. Today we're talking about rolling motion. So what I have going up on the slide right now is it's just making a red line that tracks the position of one spot on the edge of a wheel as it rolls along, right? This is a wheel rolling without slipping. So I want you to note the shape this makes. It makes kind of a weird shape, right? It's not a circle. In fact, this shape has a special name. It's called a cycloid. And it is not a circle. It's not like a sine or cosine. It can be expressed in terms of some of those things, but it's much more complicated. And the thing to notice here is notice how fast this point moves to the left or to the right as it goes across the screen, right? So right at the top of the arc, you'll notice the point is moving really fast. And at the bottom of the arc, right when it touches the ground, it actually stops moving for a split second. The velocity actually goes to 0 right when it touches the ground. So we'll talk more about that, but it's kind of a cool shape. And the cycloid turns out to be a famous shape for a number of reasons in physics. All right, so course stuff to be aware of. Here's what we have coming up. For Wiley Plus, we've got the chapter 11 homework and adaptive practice that are due on Friday. And we've got the chapter 13 adaptive practice that's due next Friday. And just as a reminder, next Friday is the hard deadline for all Wiley Plus. Okay. We have one more perusal reading left. That's on harmonic motion, and that's due Friday. So that's coming at you fast. But today or tomorrow, hop on, do some reading, leave some comments. Harmonic motion is going to be the last topic we cover. Sadly, we're not going to get to Newtonian gravity, which breaks my heart a little, but such is life. And then in terms of the video experiments, the last 2 video experiments there's one on static equilibrium, which will go up right after class today. It's actually not a video, there's just an image. And then there's another one on harmonic motion that'll go up on Friday, and that's it. As a reminder, the video experiments are all due a week from Friday. That's May 8th. So if you want credit for a video experiment, you got to submit it. The last thing to just be aware of is that you need to sign up for a time slot for the final. I think 12 of you have done that so far, and I suspect it's probably most of the people that are actually on this video chat right now. But in case you haven't, go ahead and do that. Several people have commented they don't know their final schedule. I have not been able to get a response from anybody in the university on that. They have not posted final schedules, and I don't know why. And I can't get anybody to tell me when they're going to post final schedules or if they're even going to. So do your best, find a time slot. If you have to change, we can change. That's very workable. Okay, questions about any of this?
So the video labs or the labs, they're all due May 8th?
That is the final deadline. So you should, I would encourage you to be turning them in as you go, right? But yeah, May 8th is the last day you can turn. May 8th is the last day you can turn anything in for this class. Maybe is a good way to put that. Okay, let's talk about actual physics. So this is one of the more iconic scenes in all of movie history. So this is the scene from Indiana Jones where he's escaping the tomb. So have a watch. All right, so you're scientists and engineers. I want a performance review on the Boulder security system design. How'd it function?
Not great.
Not great. Didn't get him, right? You need faster boulders. So here's the physics question. You are designing a tomb security system, and you want to have a spherical boulder that will be rolling down a tall hill at Indiana Jones. You want the boulder to have as large a velocity as possible at the bottom of the hill in order to catch intruders, like Indiana Jones. Which of these would increase the velocity of the boulder? All right. All right, I'll give you another 10 seconds. Going once, twice, sold. All right, we had a nice distribution there. I'll let you see the results. So, most people liked B, but we had some A's and C's and a D in there too. So, we'll start with B because that was the most popular. So if you decrease the boulder's radius, why would that make the boulder go faster?
My thought was it would just decrease the moment of inertia.
Okay. And if you decrease the moment of inertia, what happens?
It's easier to start rolling.
Easier to start it rolling. Okay. Anybody else like that option? Well, 3 of you did. All right. Anybody want to argue for A? A is the opposite, right? Increase the boulder's radius.
So I said A, increase the boulder's radius because it would travel farther because of the arc length.
Right. So each roll would go further. Okay.
But I partially agree with Davey because of the mass.
All right. Anybody want to argue for C or D, changing the boulder's mass? Nobody? All right. So how can we figure this out? if we want to actually check this thing, how would we figure this out?
I wrote like an energy equation.
Okay. Let's take a look at an energy equation here. So let me stop sharing that thing and come over here. And we'll take a look at this thing. So what does our energy equation have?
So I'm assuming they just like pry the big ball or something with gravity.
Right? So there's our setup, right? What energy does the ball have at the top of the hill?
MGH.
Yeah, it's got
Okay.
gravitational potential, right? So it's got MGH at the top. How about at the bottom?
Kinetic.
Kinetic, right? So it's got some translational kinetic energy, right? Because it's moving down the hill. And it's got some rotational kinetic energy. So what do those look like?
1/2 mv squared.
Yeah, 1/2 mv squared.
And then isn't it 1/2 I angular velocity squared?
Yep, 1/2 I omega squared. Okay, what's the moment of inertia for a sphere? Well, Google knows, your book knows. I know because I've been doing this long enough. The moment of inertia for a sphere is 3/5 mass of the sphere times its radius squared. I'll use lowercase m because that's what we use somewhere else, right? Okay, what happens if I put that in here? Well, I've still got the 1/2 mv squared, but now I've got 1/2 times 3/5 mass radius squared omega squared. All right. Now what do we do?
Wouldn't you just look at the variables that would affect the kinetic energy the most to increase the speed?
Yeah, so well, first of all, we can put the MGH over here, right? Because we're saying that the potential energy at the top is equal to the kinetic energy at the bottom. Okay.
We could get rid of all the M's.
We can get rid of all the M's, which means
That-
that changing the mass won't change anything, right?
Yeah, that eliminates an option.
Because now mass isn't in there anywhere. All right, but now we do have velocity over here, right? But what about this bit with the r omega? Because that's kind of something that has to do with velocity, right? The faster the boulder's spinning, the faster the boulder would be going down the hill. Does everybody agree with that?
Yeah.
So how does this relate to the boulder's velocity?
If you decrease the radius, you have to increase the angular velocity, and then vice versa.
To keep it going at some velocity, right?
Yeah.
Yeah, because if you remember, the velocity is just omega times r, which means I can replace this piece with just v squared. Which means now if I rewrite this thing, I get gh equals 1/2 v squared plus 3/10 v squared. And if I keep going to solve this thing for v, because that's what I want to do at the end, right? I can factor out the v squared. I get 1/2 plus 3/10. Oh, if I do my fractions right, 1/2 is 5/10. So I get 8/10, which is the same as 4/5 v squared. And that means that v is just the square root of 5gh over 4. Okay, so does changing the radius do anything?
No.
No, and that's the interesting thing, right? Because Davey was absolutely right. It did change the moment of inertia. And Luis was actually right too, because it also changed how far it went every time it rolled. But it turns out that those two things completely cancel each other out. And so
Look.
for rolling motion, the radius doesn't change the speed at the bottom of the hill.
Yeah, but what's also tricky is a little rock's not gonna do no damage.
Well, that's true, right? So, if you rolled like a
A marble.
marble down the hill, it's probably not going to stop Indiana Jones. All right. Now, here's the
You
follow-up
slippery
question.
hill.
Here's the follow-up question. Where'd my cursor go? All right. So now you're still designing the boulder ramp, and you still want to make its velocity as big as possible at the bottom of the ramp. Should you make the ramp as frictionless as possible, or make the ramp have as much friction as possible in order to make sure the boulder rolls, or that both of these would have the same effect on the boulder's velocity at the bottom? So let me relaunch the poll. All right. All right, I'll give you another 10 seconds. Going once, twice. Sold. All right. Most people said A. Most people are right. So give me the argument. Why is it you want to make the ramp as frictionless as possible?
My thought was just that like gravity will have the most acceleration if there's less friction I have to overcome.
Yeah. Okay, so your argument is that friction slows you down, right?
Yeah. Yeah.
So what about rolling friction?
Yeah, because of rolling friction, that's why I chose B, because I was thinking about like tires. So if you have like kinetic friction, in other words, the tire spinning, I assume maybe it wouldn't pick up as much velocity. Versus if it had friction, it'll be like static friction. It'll be able to move forward more
Yeah.
easily.
So static friction, right? So when you're rolling, you don't have kinetic friction. The two surfaces aren't sliding past each other. You have static friction. Okay. So I said the right answer was A. Let's go back over here to our energy equation and look at what happens if we change it a little bit. So if we come back up here, right, and I'm going to, let's do this in a different color. Let's come back up here to our energy at the bottom of the hill, okay? If we're not rotating, if we're sliding down the hill, right, if it's as frictionless as possible. What does that mean for this term over here? Our rotational kinetic energy term.
It's close to 0.
It's going to be 0 or really close to it, right? The boulder's still a sphere, so it's probably still going to roll a little bit, but just a little bit. Okay? Which means that if this term is really, really small, this term has to be bigger, right? If we kept energy. Now, there's a little bit of nuance here because as we slide, we are losing energy, and we'll talk about that in a minute. But when we're sliding, what does that mean for our, if we were to talk about the work done, right? The force over a distance, right? We've got a force, some friction force going uphill, right? And some distance going downhill. So we lose energy. Okay. If you're rolling, on the other hand, you don't lose any energy. Now, why? You still have friction, right? If there's no friction, you can't roll. Anybody who's ever tried to drive on ice knows that, right? If you have no friction, your tires don't roll, they skid. They
It's quite
slide.
scary.
Yeah, and it
What's
terrifies you.
What's the question again?
So here's the question. When you're rolling down the hill, you still have friction. But I'm going to argue that that friction doesn't do any work when
That's
you're
because-
rolling.
Isn't that because the contact with the ball in the ground is static friction because it's not moving?
Right. Because the point of interaction is not moving, right? It's not, there's no movement there. And so that friction, as you roll down the hill, it does make you roll, but it doesn't do any work on you.
So there's work on the other friction? I mean, on the other side of the kinetic?
Yes, because you're sliding down the hill. Because there is movement between the surface and the boulder, right? At that point where they touch, they're sliding against each other, which means that there is a displacement. The force does act over a distance. Whereas when it's rolling, there's never any velocity there, right? So there's no distance for the force to act on. So anyway, these are just kind of fun questions, right? Because obviously it depends on how frictionless you can make the ramp, and because if you can make it perfectly frictionless, then sliding is way faster. But of course, perfectly frictionless surfaces are hard to come by. And so practically speaking, you have to figure something else out.
Can you explain why you mentioned work and what it has to do with?
Yes, I
With,
can.
I don't know what we were trying to get at. It confused me.
So energy conservation, right? Saying the potential energy up here is equal to the kinetic energy down here is only true if there hasn't been any work done on the system, right? If I push the ball down the hill, I give it some extra velocity, right? I do some extra work on the ball, so its kinetic energy would get bigger at the bottom. Similarly, if I have kinetic friction as I slide down the hill, that kinetic friction would do negative work on the ball as it rolled down the hill, which would decrease its kinetic energy. Okay? But here's the trick. So here's my point. Rolling motion is a special case. In rolling motion, so these are the things we know about rolling motion. Okay? Number one, rolling motion only has static friction, which means there is no energy loss, which is the same as saying no negative work. Okay, because remember, negative work is taking energy out of a system if it's negative, it's putting energy into a system if it's positive. When we have the static friction here of rolling motion, it does no negative work. There's no energy loss or gain, but there's no loss of energy from static friction in rolling motion. Does that make sense?
Yeah.
This is why everyone knows that you would much rather put something on a wheel and roll it across the surface than drag it across the surface, right? Because by putting something on a wheel and letting it roll, you get this no energy loss, right? It's why your bicycle works so darn well. Why you can go so much faster on your bicycle than you can by running. Because when you run, there's a lot of kinetic friction, right? Every time your foot hits the ground, there's a whole bunch of friction going on. But when your bike tire rolls, it only has static friction, which means you don't lose energy from the rolling itself. Okay? So that's one of the benefits of rolling motion. Let's talk about another one. We'll come back to this paper because there are more things we want to note about rolling motion. We've talked about this before, but if I have an object and it's rolling, okay, the velocity at the point where it touches the ground has to be 0. Because that's what rolling motion means. Rolling motion means that I am just moving fast enough so that I'm not sliding, I'm not skidding forward or backwards as I move across the ground, which means that the velocity here has to be the same. So this means that I get a total velocity of 0 at the bottom, okay? But not 0 at the center, right? If I look at the center of the wheel is going over with some velocity, we'll call it V naught, right? The velocity of the whole wheel, right? So what does that mean up here? What's the
Doesn't
top of the wheel doing?
Wouldn't it have -2 V naught for its velocity?
Negative or positive?
Negative because it's moving, or positive.
You wanted to go in that way?
Or I was thinking.
Yeah,
about
this way.
+2. You know.
Yeah, it's got twice the velocity. Its total velocity is twice up at the top. And that's why we get that funky shape that I was showing you at the beginning of class. Because as you track a point along here, it goes from not moving at all when it touches the bottom to moving twice as fast when it's up at the top, to back down to 0 at the bottom again. Okay, so this is weird, right? Different parts of the wheel are moving at different velocities. But we can actually explain this in a fairly simple way. What's going on here is that we have two types of motion overlaid on top of each other. The whole wheel is translating at speed V naught. Okay? The whole wheel. The bottom, top, middle, right? The whole thing is moving at that speed. And on top of that, I have overlaid a rolling motion, right? So it's rolling this way, which means at the bottom, my velocity is negative omega times r, right? Omega is the rotation rate, and r is the radius of the wheel. In the middle, I don't have any r, right? So I have 0 rotational velocity. And at the top, I'm moving, let me draw it down here. I'm kind of out of space. We'll just draw it over the top of things. I'm moving to the right again at omega times r, which means this can all work out as long as my velocity equals omega times r. Okay? So that's our second piece of rolling motion. In rolling motion, our angular variables and our linear variables are related in a nice simple way. Our velocity is just equal to our angular velocity times the radius, and our acceleration is just equal to our angular acceleration times radius, and the angle we travel through, I'm sorry, I'm right it the same way. And the distance we travel is just our angle times radius. Okay? So in rolling motion, in order to make it rolling motion, these things have to be true. Okay? How are we feeling?
Are all these what's it called? I don't know if to call them vectors or not. Are they all like perpendicular?
Okay, so these are
The
all,
W times R?
the way I've written these, they're not vectors. I'm talking about the magnitude of the velocity. So the speed is related to the angular velocity times the radius. And the magnitude of the acceleration is the angular acceleration times the radius. Now, I could do this, I could write these things as cross products and do the vector bits, right? But here I'm just writing them as scalars. And so I'm talking about the magnitudes, okay? Does that make sense?
So these are all the magnitudes.
Yes. So I'm talking about the magnitude of the velocity vector is equal to the magnitude of the angular velocity vector times the magnitude of the radius vector. And the same is true for all of these, right? Okay. So here's the next piece about rolling motion that we're going to think about. So what I want you to do, let's come over here. So a number of you have already looked at this. And this is, I want to make a point that what we're going to talk about here, we're going to use the same data we used for the moment of inertia video experiment, but I'm not asking the same question, okay? So you guys have hopefully seen this. I only really want to show you the piece where the actual ball rolls down. And where are we? Here we go. Okay. So what we want to do here is have the ball roll. We're going to let it go. Okay. Not very exciting, right? Ball rolls downhill. But the nice thing is that we have data on this, right? We're collecting data. So if I come over here and I look at the data for this, maybe. All right, so here's the graphical analysis file. So this measured the distance from the top of the ramp that the ball that the ball was as a function of time. Okay. And it looks like a parabola, right? If we look at this range of data here, it looks very much like a parabola. And it should, right? We did this like 18 times at the beginning of the semester, where we roll the cart down a hill and we measured its position, and we found that, you know, it was related, that it had an acceleration equal to g sine theta, right? Okay, so for this particular setup, let's see here. For this particular setup, our angle, oh, come on, where's my angle? Oh, goodness. Hold on one sec. Now I've lost my angle. Come on. All right. You have to give me just a minute because for some reason I am not finding this thing. My goodness, did I? Oh, 5 degrees. It's a 5-degree ramp. Okay. So how fast should the ball accelerate down the ramp if it weren't rolling, right? If it were just a block sliding down an inclined plane, no friction, how fast, or what would the acceleration be?
Wouldn't it be gravity times sine of 5 degrees?
Right, which is, all right, somebody bust out Google. 9.8.
What was that? Gravity times what?
Times sine of 5 degrees.
Times the sine of 5 degrees, he said. Okay. So how fast, so what acceleration would we expect?
0.85 meters per second squared.
Yep. So 0.85, which means if I look at my graphical or my data here and I fit a parabola to it, right? I say apply curve fit. I want a quadratic. I hit apply. I get this coefficient A of which is related to my acceleration. It's not my acceleration, remember? It's actually 1/2 times my acceleration. But if I double that, I get an acceleration of 0.49 and change meters per second squared, which is pretty noticeably different than 0.85. So what happened?
It was because it was rolling.
Because it was rolling, right? It was rolling, which means that we talked about it in terms of energy, but now I want you to come back and talk to me about this in terms of force. If it had less acceleration, what does that mean about the force on the ball?
There was less force acting on it.
Right, there had to be. There had to be less force because the only way to get less acceleration is to have less net force. So here's how we get less net force. Now, by the way, let's keep track of this. So we measured the acceleration of the ball to be 0.49 meters per second squared. Okay. So let's keep track of that. All right. Let me stop sharing this screen and start sharing this one again. So what happened is that we got a make write out the forces on this like is shown here, right? So we have the ball. It starts at rest. It's allowed to accelerate down the slope. Okay, if we drew all of the forces, right, we have a normal force, which is acting where it touches, right? We have gravity, which we've broken up because we've chosen to make our coordinate system x is pointed downhill and y is pointed out of the ramp, right? So we have an mg sine theta force going downhill. We have a negative mg cosine theta force going into the ramp that's balanced by the normal force. And we have this guy. What's that? What's this lovely little force right here?
Friction?
It's friction. And it's acting where the ball touches the ramp, which means that it produces what? In addition to a force, there's also a what associated with it?
Acceleration?
Right? So it will change the acceleration because it's a force. But what else does it do?
Is there a torque?
Yeah, there's a torque because it's not located at the center of mass. The torque, it has a lever arm, right? So it wants to make the ball spin as it rolls down the ramp. Okay, so this brings us to our other point about rolling motion that we should keep track of. So let me stop sharing that and come over here. Okay. When we talk about rolling motion, you need a balance between the force and the torque. Okay? Because if we think about that diagram, if I have too much force going downhill, right, then I will slide instead of roll. If I have too much torque, I will roll, I will skid out, right? I'll peel out. My ball will start rolling faster than it's actually moving down the hill. So I need a balance between the force and the torque. And I can get that balance from this equation right here. Okay? Newton's second law tells me that acceleration is the sum of the forces divided by the mass. Okay? Which in this case, we've got gravity going downhill, mg sine theta going downhill, and we've got some static friction force going uphill divided by mass. And that has to be balanced out by, well, the radius times, and I know from the rotational version of Newton's second law, that this is just the sum of the torques divided by the moment of inertia. Okay? Well, in this case, there's only one torque, and it's from the friction. And so if I rewrite these equations, I'm going to get mg sine theta minus my friction force divided by mass has to equal R times, now I've got to figure out my torque. So first question to ask, is my torque pointed, or is my torque applied, or what is the angle between the radius vector and the force vector?
It's perpendicular.
Right, it's perpendicular, which means I can save myself a lot of headache on that cross product. And just write this as my radius times my force divided by my moment of inertia. Okay, what's happening here? I've got friction over here, and I've got friction over there. So I'm going to end up with some kind of a relationship between the friction force and the force pulling you downhill, which I'm actually going to stop writing this as mg sine theta because this works for any rolling motion. So I'm just going to call this the other force, right? I'm going to call it, FO because it's the other force, okay? So if I take some things apart here, I can do one other thing. Moments of inertia for round objects always have what form?
Some number r squared omega squared.
Not omega squared, but m. They have some number, which I'm going to call, c times m r squared. Okay? For a thin hoop, c is 1. For a cylinder, c is a half. For a sphere, it's 3/5. For a pick your shape, right? All it does is change the c. It doesn't change the m and the r. So if I put that in here, what I'm going to get is something that looks like my downhill force or my forward force, I'm going to call it, divided by my static friction force over m equals r squared friction force divided by some constant times m r squared. The r squareds cancel and the m's cancel. And what I'm left with is my condition here, which I'm going to write in a different color. And that is that my downhill force has to equal, okay, I move this friction force over to the other side. Well, let's just do that over here. If I move the friction force to the other side, I get friction force over c plus friction force, which means that this equals my downhill force has to equal my friction force times 1 plus 1 over c. Okay? So there has to be a balance. And this is what the balance is. The downhill force has to be related to the friction force. Now, how on earth do you balance that? Because it seems like rolling happens a lot without things being perfectly balanced of how much friction you have. So explain this to me. How can this be true? That there's this very careful, deliberate balance between the friction force and the downhill force. What kind of friction is this?
Static.
Static friction. So is there static friction between that pen and that paper right now?
No, because there's no forces on the pen.
Ah, but what if I push the pen a little bit?
Now there is.
Now there is. So what happened? Why did it go away when I stopped pushing?
Because friction always opposes the forces.
Right. Because static friction only tells you how much force you could possibly have. right? It doesn't tell you how much force you actually have. You actually have whatever force is needed to keep two things from sliding relative to each other. That's all static friction does. So when you're rolling, your static friction force always balances itself to match against the downhill force or the force pushing you forward. Okay? Up to some point. Now, there's a limit to that, right? At some point, if you try to push forward too fast, you can't, right? Your static friction isn't enough. When does that happen? Give me a real world example of when you try to have too big of a force and your static friction can't keep up.
When you put on your brakes and they lock.
Right. If you lock your brakes, okay? If you skid on a bike tire, if you peel out, okay? In all of those cases, the static friction wasn't enough to overcome the other forces acting on it. And so you didn't roll, you slid or skidded or the tire moved, right? The point of touching moved. But here's the handy thing. What this means is we can tell what the static friction force is just by looking at what happened over here, right? Because what happened over here doesn't have anything to do with anything other than the shape of the object, right? That C comes from the shape of the object. So let's go back to our example with the ball rolling down the hill. Anybody know off the top of their head what C is for a sphere? I'm
Three-fifths.
sorry, for a thin spherical shell?
One.
For a ring, it's 1. But for a spherical shell, it turns out it's not. So here's what I want you to do. I want you to open up a new tab, and I want you to Google moment of inertia, thin spherical shell. All right, so what's the moment of inertia for a thin spherical shell?
Two-thirds.
2/3. It's 2/3 mr squared. Oh, by the way, it looks like I screwed up the sphere. A solid sphere is 2/5, not 3/5. Sorry about that. I can tell you're all very upset. All right, but a thin spherical shell is 2/3, right? So that means if I come over here and I think about my rolling object, my ball rolling down the hill, okay? That means that the force going downhill has to equal the force of friction, the static friction, times 1 plus 1 over 2/3. Or in other words, my force going down the hill has to equal the magnitude of my friction force times, what's 1 plus 1 over 2/3, fraction people?
5/2.
Yep, because we just put the 3 up here, we get 3/2. 1 plus 3/2 is 5/2, right? So this is just times 5/2, which means I know what our static friction force had to be. It had to be 2/5 of my other force, right? The one going downhill, which is just mg sine theta. Okay? So now if we go back to our diagram, now we know what this friction force is, right? We know what it had to be because the ball rolled. So just by the fact that it rolled, we know what the friction force was. It was 2/5 of this force, which means how much of this force was left?
3/5.
3/5. So we guessed, or if it had slid down the hill, it would have had an acceleration of 9.8 times the sine of 5 degrees, which comes out to 0.85 meters per second squared. If I multiply that by 3/5, what do I get?
About 0.5.
About 0.5. What did we say we got from the curve fit?
About 0.5.
About 0.5. So it works, right? Okay, so rolling motion is this weird special case where everything has to be just right. And it seems like that would make it hard to do, but it turns out it's not hard, it's extremely easy. Because as long as you have enough static friction available, everything wants to roll. Everything wants to roll. As long as you have enough friction available. Now think about that statement for a minute. We almost always think of friction as the enemy, right? Friction is what makes life harder. But here's the fun thing about rolling motion. Rolling motion, friction is what makes life easier. Because you'll only have as much of it as you absolutely need. Okay? Here's the other cool thing about this. So that relationship I just gave you, right? That the friction of the other force, right, is equal to the static friction force plus 1/1 plus that geometric constant, right? What does that mean if we're just rolling on a level surface, right? If I make this, let me hold on. If I make this force go away, right? So instead of rolling down a hill, we're just rolling on a level surface. What does that mean for this guy?
Doesn't that mean that the friction will just slow it down?
Would it? If I make this other force 0, what did that
It'd be
relationship?
0.
Yeah, the friction goes to 0. So the friction force goes away if you're not accelerating, right? And the friction force goes away. I mean, it just doesn't need to be there anymore, so it's not. Okay? So rolling motion is this it almost seems magical to me, right? That it all just works. That something as simple as saying, okay, they have to roll together, right? That we have to roll in such a way that the point on the bottom doesn't slide across the ground, right? That it results in all of these really cool sorts of things that pop out of it. It results in the fact that you can make friction your buddy, right? It results in the fact that the friction force goes away if you're not trying to accelerate. Even though the surface hasn't changed, right? That's the crazy thing to me, because we always think of friction depending on the surface, right? But what I'm saying is, in this case, in rolling motion, the friction, as long as there's enough of it, it doesn't depend on the surface. It depends on what you're trying to do to the ball. If you're trying to make it speed up or slow down or just roll along, that will change what the friction force is doing. Okay, should we do an example?
Yes.
Great. Let's talk about yo-yos. So, a yo-yo works because it rolls down the string. Okay? So here's what I want to figure out. I've got a yo-yo. It has a mass of 100 grams and it falls without slipping against the string attached to it. The top end of the string is held on your finger at a fixed location. The yo-yo is roughly a cylinder with a radius of 8 centimeters, and the string is 1 meter long. How long will it take the yo-yo to reach the end of the string if it starts falling from rest? Okay, so let's draw this thing. All right, here's my yo-yo. So a yo-yo is just rolling downward, right? Which seems like a weird thing to say, but it's exactly what's happening. It's rolling down the string. So let's draw a little blow up over here. What forces are acting on my yo-yo as I roll down the string?
Gravity, and then gravity from the center, and then friction from the side that the string's attached.
Yeah. So we've got some gravity in the center, right? And we've got some friction force, or you could call it a tension force, or you could call it whatever you want, right? But it's the force from the string. So I'm going to call it S, because that's where it comes from. Whatever you want to name it, right? Okay. And we know it's rolling, which means we automatically know a few things, right? We automatically know that its acceleration is related to its angular acceleration times its radius. And we automatically know that that other force, which in this case is gravity, is related to the string force by that lovely little formula. Okay. All right. So what is it? So we said the yo-yo is roughly a cylinder. So for a cylinder, what's the moment of inertia? All right. Open the new tab, punch it into Google.
One half mr squared.
There we go. 1/2 mr squared. Okay, so the C is 1/2, right? That just depends on geometry. So I automatically know that there's a relationship here. And I can rewrite this instead of writing it as FO, right? This is gravity, which is just mg is equal to my string force times 1 plus 1 over C, which is 1 over 1/2. Or in other words, so now I already know that my string force, because this is 1 over 1 plus 1 over 1/2. So this is 2, so it's 3. So it's 1/3 mg. Okay. So now I can just write out Newton's second law, right? Newton's second law says that the acceleration is the sum of the forces divided by mass. I've got mg going down, and I've got 1/3 mg going back up, and I divide it all by m, which means that my acceleration has got to be, well, my m's cancel, and I end up with g minus 1/3 g. So I end up with 2/3 g. So now what do I do? I've got my acceleration. What do I want to know at the end of this problem?
What was it asking for again?
Oh, it was asking for, oh, okay. So the string is 1 meter long. And I want to know how long it takes to get to the bottom of the string, right? If I drop my yo-yo, how long does it take to get to the bottom of the string? And if I do that, right, I'm going to get, so now what do? I know my acceleration. I know how far I want to go. I want the time.
So you need the velocity?
Yeah,
Right.
this is a kinematics problem, right? I can integrate this thing and go to velocity. So that means that my velocity is a function of time. Looks like 2/3 g times t plus my initial velocity, which is 0. And that my position as a function of time is just 1/2 times 2/3 g times t squared plus my initial position, right? Which I'm going to call 0. And I want to know how long it takes me to get to 1 meter, right? So I just solve for t. So t squared is going to be equal to my distance, my delta x over g. And then I'm going to end up with a 3 up here, right? So that means that my time is just the square root of 3 delta x over g, which means that if I plug in my numbers, right, I've got 3 times a meter divided by 9.8. Take the square root of that. Voila. So what does the yo-yo do? The fact that it's attached to the string, what does that do to it?
I think I got a different quote. 1/2 times 2/3, wouldn't that be 2/6?
1/2 times 2/3, so the 2's are going to cancel here,
Oh, okay. Never
right?
mind.
You got a 2 in the denominator, 2 in the numerator, so you're just left with 1/3, which, by the way, is 2/6. So you're right.
I
Yeah,
didn't
you're right.
reduce it.
Yeah, but it's the same deal, right? Give you the same answer if you plug it into a calculator. Yeah. So the yo-yo effectively just makes it drop slower, right? So a yo-yo is basically just a toy to play with moments of inertia and rolling motion, right? And then you can use the fact that it has some kinetic energy at the bottom, some rotational kinetic energy to make it do funny things, right? All right, how we feeling? Okay, so there's obviously, so rolling motion is this kind of fun sort of way to wrap up this segment we've done on rotational dynamics, okay? Because rolling motion combines a lot of the things we've done all through the course of the semester. We have to think about static friction. We have to think about the relationship between the angular variables and the linear variables. We have to think about a balance between forces and torques, right? And all of those things change the way that we work through this rolling motion, and they lead to these really simple but really sort of just surprising pieces. So we'll call that a class for today, unless there are any other questions. All right. Remember that there's a perusal reading for Friday, and I'll be around today after class for questions. And if you have questions, you can also catch Sean Tomorrow he's got office hours. Please shoot him an email if you are planning on coming to office hours tomorrow, so that he knows you're coming. But yeah, other than that, have a good couple of days, and I will see you on Friday.